Welcome back to Conceptual Physics using Paul Hewitt's Conceptual Physics book. Today we are talking about Newton's first law of motion. Our story starts with Mr. Aristotle, who lived in the 300s BC. He was kind of the expert on motion for many years. His word was taken sort of as truth. And what he said about motion was that there are two kinds of motion, natural motion and violent motion. Let's first look at natural motion. What Aristotle said about natural motion is that every object has a proper place determined by its nature. So there were four kinds of nature: earth, air, fire, and water, evidently. And any object not in its proper place will strive, quote unquote, to get there. This is what Aristotle said about natural motion. So let's take, for instance, smoke. Smoke is made of air, and air belongs, according to Aristotle, in the sky. So smoke, its natural motion will be to rise. A lump of clay is made of earth. Earth's natural position is on the earth, so a lump of clay will drop down to the earth. That's its natural position, and it will strive to get there by falling. A feather, evidently, was kind of a combination of earth and air, so while it strove to get to the ground because it had earth in it, it also had air in it, so it fell slower. Again, this is what Aristotle said. Spoiler alert, this is not what we know today. All right, so he said heavier objects strive harder. The heavier the object, the faster it should fall. So that was another attribute of natural motion. So let me just reiterate what Aristotle said. The heavier the object, the faster it should fall. Again, spoiler alert, this isn't what we know today. Let's look at violent motion. Aristotle said that violent motion results from pushing or pulling. Objects move not by themselves, but because of sustained pushes or pulls. In other words, with violent motion, according to Aristotle, if something is in its proper place, it won't move unless it's subjected to a constant sustained force, unless something is pushing or pulling on it. Provided an object is in its proper place, it won't move unless subjected to a force, a sustained push or pull. The normal state of any object is at rest. So here's what Aristotle said. Just to reiterate, an object will slow down and stop unless there is a constant force acting on it that causes it to move. Let's try it. Go ahead, get up, find something kind of heavy, and move it across the floor. Go ahead, don't sit there, get up, move something across the floor. Did you do it? I'll wait. Now, did you do it? What happened? If you stop pushing that object, does it keep on moving? No, it doesn't. Unless you're standing on ice or something like that. Aristotle in this case seems right. Whatever you pushed across the floor, I've pushed lots of things across the floor. I just pushed my physics book across the floor. Or maybe you pushed a desk across the floor. Once you stop pushing it, that thing stops. All right, now let's walk across the room. Go ahead, get up, walk across the room. What did you just walk through? There's some substance that you walked through when you walked across the room. That's right, air. You walked through air. When we move on Earth, or when anything on Earth moves, it moves through something like water or air. Now, Aristotle just couldn't imagine a case where this wasn't true, like in outer space where there is no air. Here is a guy who could imagine a case where there was no air. Enter Mr. Galileo Galilei. He lived from the 1500s to the 1600s. Galileo did some really interesting things with balls rolling down slopes or inclined planes. Just to simplify what he did, he rolled a ball down a downward slope and he noticed that the speed of the ball increased. He did the same thing. He rolled a ball on an upward slope and he noticed that the speed decreased. So on a downward slope, the ball sped up. On an upward slope, the ball slowed down. What would happen then on no slope, a flat surface? If a ball speeds up on the way down on a downward slope and slows down on the way up on an upward slope, what will it do on no slope? Galileo reasoned that on a horizontal plane, the ball will neither speed up nor slow down. So if the ball is speeding up going down, and if it's slowing down going up, then the exact middle there is neither speeding up or slowing down. The ball will just keep going at the same speed. That's what Galileo reasoned, which was revolutionary. It really, really differed from what Aristotle said because Galileo said that if the ball came to rest on that horizontal surface, it would come to rest because of friction, not because of some weird esoteric nature or some natural nature of that object. It came to rest because of friction. And you can try this. Roll a ball on different types of flat surfaces. Maybe try it on a carpet and then try it on a hardwood smooth floor or a tile floor. And you'll see that on the carpet where there's more friction, the ball will slow down and come to a stop faster than a surface that's smooth and has less friction. So, what Galileo said is, in the absence of retarding forces like friction, the tendency of a ball on the flat surface is to move dun 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 forever without slowing down. That was the big, huge, enormous, revolutionary concept that Galileo gave us. He said things come to rest because of opposing forces like friction. Remove all those opposing forces, and something that is set in motion will keep moving forever. Galileo came up with a term to describe this concept. He said that the property of an object to keep moving straight ahead is inertia. He called that property of an object to want to keep moving straight ahead inertia. I just want to emphasize the difference between what Aristotle said and what Galileo said, because they could not be more different. Remember, Aristotle said the normal state of an object is one of rest. You know, like the little sloths wanting to be at rest all the time. Well, guess what? Not true. Remember, Aristotle said an object will slow down and stop unless there is constantly a force acting on it, causing it to move? Not true. Aristotle said a moving object must be propelled by a steady force in order for it to keep moving. Galileo said, nope, not true. In the absence of a force, a moving object will continue moving. You don't need a force to keep it moving. And then we have Mr. Newton. He took this whole idea of inertia, refined it, and made it into his first of 3 laws. We're going to concentrate on the first right now. Mr. Isaac Newton. He lived from 1642 to 1727, and he was quite the gentleman. He gave us 3 laws that sort of revolutionized how we think about motion. We are going to focus on Newton's first law right now, and here it is, ladies and gentlemen, Newton's first law. Every object continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. There you have it, Newton's first law. Now, in that law, there was a word forces. What is a force? Well, quite simply, the easiest way to think about it is a push or a pull. If someone pushes you, they exert a force on you. If someone pulls you, they exert a force on you. So it's just the easiest way to think about a force. Now, there were a couple of cases inside of Newton's first law. One was when an object is in a state of rest. The other was if an object is in uniform motion in a straight line. In other words, if it's going at a constant speed in a straight line. And according to Newton's first law, a body at rest has a tendency to want to remain at rest, and a body that's in motion has a tendency to keep moving once it's set in motion. And with each of these cases, the at rest case and the moving case, there's some amazing, awesome, very cool examples in our everyday lives. Let's start with the at rest case.
Mom, I set the table for dinner.
You did? Oh, that's great! Oh, I'm so glad she set the table for dinner. Oh, that looks so nice, but I don't like that tablecloth. Much better.
You just saw an example of something at rest wanting to stay at rest. Now let's look at an example of something in motion wanting to stay in motion.
God, this ketchup bottle's kind of low. How am I going to get this ketchup out? Ah, Newton's first law. Perfect. Oh man, this barbecue sauce is low. How am I going to get this out? Ah, Newton's first law. Works like a charm every time.
There's so many other examples of inertia in our everyday lives. Here are just a few. One is skiing. Any activity really that involves snow or ice where friction is small. Ice skating, playing hockey. That hockey puck, once you hit the hockey puck, it slides across the ice and doesn't really slow down until it hits a wall or hits someone's hockey stick. Air hockey is another awesome example. If you've ever played air hockey, friction is really, really small on that air hockey table. So once you hit that puck, it just keeps on moving until it hits the edge of the table or until it hits the other person's air hockey thingy. Seat belts are another great example. When you're moving in a car, as you're driving in a car, and the car stops suddenly, well, you were moving, and just because the car stops doesn't mean that you stop too. You want to keep moving. You have inertia. You want to keep moving. The seat belt is what keeps you from just moving forward and moving right through the windshield of the car, for instance. I love to eat watermelon, and sometimes I'll leave watermelon in the trunk of my car as I push on the gas pedal. Let's say I'm stopped at a red light, and I push on the gas pedal. The car starts moving, but the watermelon was still and wants to stay still. So it ends up rolling backwards in the trunk of my car. Or if we're moving and then I stop, well, the watermelon was moving and the car stops, but the watermelon wants to just keep going, so it'll roll forward in the trunk of my car. So because of inertia, I have watermelon rolling around in the forward and backwards in the trunk of my car. Look for examples of inertia in your everyday life. There are so many of them, and once you start to notice them, they're everywhere and they're really cool to see. Hope you enjoyed this video learning about Newton's first law and inertia. We'll see you in the next video.